Previously we discussed linear models, so our next topic is quadratic models. Quadratic models have the following characteristics. In a table of values, the average rate of change increases or decreases by a constant value. The graph of the curve is called a parabola. And the equation can be written in the form y equals ax squared plus bx plus c, where c is the vertical intercept. So you should be able to identify a quadratic model by its table of values, by its graph, or by its equation. So example 1. Which model represents a quadratic relation? Justify your answer. So the first one, the highest exponent we have is in 2, so therefore this must be a quadratic relation. The only term we're missing is the term with the x in it, but we have the ax squared, where a is 1, and we have the c value, which is 7. B. Because of the x cubed, this is not a quadratic relation. Now let's look at our two graphs. Graph in example C is a parabola, so this is quadratic. And similarly, in part D, it could also represent a parabola. Both C and D are quadratics. And finally, for our table, we want to look for the AROC, so the average rate of change. And when we take out the first cell, we're going to subtract the two y's, delta y, over the delta x. So we have 238 minus 250 over 1 minus 0. Using our calculator, we should get an average rate of change of negative 12. Go over, subtract above, delta y over the delta x. So 202 minus 238 over 2 minus 1. And this gives us negative 36. And if you try the last one, you should end up with negative 60. Since the average rate of change varies, this is not a linear relation. However, we do see that these numbers are going down by negative 24. So the average rate of change is decreasing by the same value. Therefore, this is quadratic. And for part F, since we have a table, we need to find the average rate of change. So again, delta y over delta x. So 48 minus 32 over 5 minus 0. Using your calculator, you should get, you will get 3.2. Going over, delta y over delta x. So that's 72 minus 48 over 10 minus 5. That'll give us 4.8. And then you can try the last one. You should get 7.2. Again, if we look at these here, this one increases by 1.6. And then to go from here to here, that increases by 2.4. So since the average rate of change varies, as well as how much it goes up by, then this is not a quadratic relation. A fountain of sparks from a Canada Day rocket follows a parabolic arch in the air. This table shows the height of the sparks at various horizontal distances from the launching point. So we're going to use Desmos to determine the equation of the parabola of best fit. So just to show you how I got this graph and how I ended up with this equation, let's go to Desmos. So first off, I typed in our values as shown over here. Then I can add my axis titles if I'd like. So our x-axis is the distance in meters. And then our y-axis is the height in meters. Next, we want to find the quadratic equation of best fit. So let's go down to our keypad. So remember from our table of values, this is y1. So we click the y, find the subscript button, go back to our numbers, type in 1, hit the right arrow, go over to the approximate symbol or the tilde, and then we need a x subscript 1, and then we need the squared on it. So there's the square button. Then plus bx, so bx subscript 1, right arrow, plus c. So click on the letters, plus c. There is our quadratic equation of best fit. And then over to the left here are the results. Here's our a value, our b value, and our c value. So here's our a value, our b value, and our c value. Our equation of best fit then is y equals negative 0.206429 x squared plus 9.49929 x plus 0.7. So let's answer the following questions. What do the variables represent in the equation of best fit? So we're going to start with the x, and we see the x represents our distance in meters. And here's the y. The y is the height in meters. C, determine the maximum height of the sparks. So we can make an estimate from the graph here and drag that over. And it looks to be about 110. We go up to the table. That does seem to be a good set of values. However, we did graph this in Desmos. So we can go to Desmos. We could click on the max value, try to find it, and notice if I click there, it says the max occurs at 23 meters in, 23.009, and the maximum height is approximately 109.983, so approximately 110 meters, based upon Desmos. What does the c value represent in this equation? Remember, that's our starting point for a parabola where it crosses the y-axis. So in this example, this would be the height at which the rocket was launched. How far from the launching point will a spark be when the spark is at a height of 50? So we're looking for the distance because in this example we're given the y value. We're told that y, the height of the rocket, is 50. So again, we can go to our graph. There's 50. And we can see there's 2 points. It looks to be about 40. And if we count there, that's 2, 4, 6. So it looks to be about 6 meters and 40 meters. That's if we look at our graph. The second thing we can do is we can go back and verify this in Desmos. So if we go to Desmos, we're going to type in y equals 50. Hit enter. Then all we need to do is click on the 2 points. So see about 5.96, so approximately 6, and about 4.055. So as we predicted by the graph, approximately 6 meters and approximately 40 meters in, the rocket is at a height of 50 meters. And part F. How high is a spark when it is 35 meters from the launching point? So let's go back to our graph. 35 meters from the launching point. So there's 30, 32, 34, 36. So in between here, it looks to hit about that height there. If we trace that over, so there is 35 meters from the launching point. The height, if we trace that over, appears to be 60, 70, 80, approximately 80. So let's go to Desmos and check that out. So this time we have x equals 35. And we hit enter. Click on the point, and notice 35 meters in, it appears to be 80.3 meters high. So the spark is approximately 80 meters high when it's 35 meters from the launching point. And remember, for this one, we're going to let x equal 35. That's the distance from the launching point. All right, so let's summarize what we've covered so far. First thing, the equation will have an x squared in it. So it looks something like this. Y equals ax squared plus bx plus c. The highest exponent must be 2. And for example, that could be y equals negative 5x squared plus 4x minus 7. From a table of values, the A rock is increasing or decreasing by the same value. So for example, if we had a table of values x, y, and here's our A rock, and we take out that first cell. If this was 2, 4, 6, we can see that these is going up by 2, going up by 2. So this would be a quadratic relation because the A rocks are all increasing by a value of 2. And the last is the graph. So the graph is a parabola. And it could be one of two scenarios. The graph can open up or the graph can open down. Please note for the work today, you will need to use Desmos for questions 12 and 14. Good luck.